Welcome to the Deep Dive. Ready to explore some data science and AI today?
Sounds good to me.
Great. So you sent us these really cool excerpts from a Korean university lecture. Looks like some pretty fascinating stuff.
Yeah. There's algorithm evaluation, bias versus variance.
Supervised versus unsupervised learning.
Yeah.
Even something about an epidemic in the 1600s.
It is a cool mix.
Definitely. And it seems like you're not just interested in the what of AI and data science, but
The how and why.
exactly. So that's what we'll be focusing on in this deep dive, how these concepts connect, why they even matter, and what questions they raise.
Like, for example, we'll look at why just asking, are you a good person, can actually make data biased.
Oh yeah, that's a good one. And we'll explore what analyzing tweets about MERS can teach us about patterns.
Plus, what a 17th century Korean diary tells us about how to interpret data today.
So much to unpack. But let's start with the basics. How did machines actually learn?
Well, the lecture uses a definition from Tom Mitchell. He says that a computer program learns if it, improves its performance at a task with more experience.
So it's not about machines like hitting the books or anything.
Right. More about getting better at a task over time.
Got it.
The lecture uses spam filtering as an example.
Okay, so how would that work?
So imagine the task is to figure out which emails are spam, right? The experience is basically feeding the algorithm a ton of emails, and then how well it actually figures out what's spam. That's like the performance measure.
So the more emails it sees, the better it gets at spotting spam.
Exactly. And that's the learning part.
Makes sense. So then what makes one spam filtering algorithm better than another? Is it all about accuracy?
Well, that's where we get into bias and variance. A good algorithm needs to have a good balance between the two.
Okay, so I'm seeing how this can get tricky. The lecture actually points out that even really simple questions can end up making data biased. They mention asking someone, are you a good person? Seems straightforward enough, but...
But it's not really, is it? I mean, how someone sees themselves, how good they think they are, it's going to vary from person to person.
Yeah.
And then you have things like cultural factors that influence how people answer.
That's a really good point. So even before we get to all the fancy algorithms and stuff, we have to think critically about how we're gathering the data in the first place.
Exactly.
And what kinds of biases might already be there.
Huge. Being aware of potential bias is like the first step when you're designing any kind of data collection.
Makes sense. Now let's talk about how machines actually learn. The lecture mentions two main types, supervised and unsupervised learning.
Right.
Supervised learning, well, kind of sounds like there's like a teacher involved.
It does. Think of it like, those textbooks with all the answers in the back?
Oh, yeah, for sure.
It's kind of like that. You give the algorithm labeled data. So like emails that are already tagged as spam or not spam. And it uses these examples to learn how to, predict the right label for new emails.
So it's learning by example, basically. Yeah.
Okay. And then what about unsupervised learning?
Unsupervised learning is more like if you're given a puzzle, but without the picture on the box.
Ooh, that's harder.
Right. You just hand the algorithm data that isn't labeled, and it tries to find its own patterns and structures.
So it has to figure things out all on its own.
Exactly. The lecture uses the example of, say, predicting crop yields. That would be supervised because you already have historical data with known yields.
Okay, I see.
But if you wanted to group spam emails into different categories based on their content, that would be unsupervised learning. You're basically letting the algorithm figure out those patterns.
Interesting. So it could find patterns that we might not have even thought of.
Exactly.
Cool. So how do we know if our algorithm is doing a good job? I'm guessing that's where model evaluation comes in.
You got it. And one of the tools we use for that is something called the confusion matrix.
The confusion matrix. That sounds a little intimidating. It's actually not as scary as it sounds. Think of it like a table. It helps us visualize how well a classification algorithm is performing.
Okay, so with our spam filter example.
Right. The confusion matrix shows us, how many emails we got right, like how many were correctly labeled as spam, how many were correctly labeled as not spam.
And how many we messed up on.
Exactly. It tells us how many were misclassified, so it really breaks down all the different ways the spam filter can get it right or wrong.
So we can see the types of errors the model is making.
Yep. And then from there, we can calculate things like accuracy, precision, and false positive rates.
And that leads to the question, how do we even know what's good enough when it comes to those things?
Good question. It really depends on what you're trying to achieve, right? Like
Yeah.
with the spam filter, if it marks a real email as spam.
A false positive.
Yeah. That can be way more annoying than if it lets an actual spam email slip through, a false negative.
So even with something as simple as a spam filter, there are all sorts of trade-offs to think about. But let's zoom out for a minute. The lecture also mentions using math functions to model, like, the whole world. What does that even mean?
So basically, it's trying to represent all the complexity of the real world with, like, simplified math expressions.
I see.
And these models are super helpful for making predictions and understanding patterns in the data.
But like with any simplification, there have to be some limitations, right?
Oh, of course. It's like when you look at a city through a telescope, you'll see some things super clearly, but you'll also miss all the little details happening on the street.
Right. And that actually reminds me of the example from the lecture, that 1698 epidemic described in the Korean diary.
Yeah, that's a good one. They assumed barbarian grain was the cause of the epidemic, but there were probably all sorts of other factors they didn't even consider.
Shows how our models can be useful, but are still just representations.
Exactly. They're not the whole picture.
Definitely something to keep in mind. So then we get to overfitting and underfitting. I'm guessing these are like potential problems when you're building models.
Yep, they are.
Okay, so what exactly are they?
So overfitting is when your model learns the training data too well, if that makes sense.
Like a student who memorizes the textbook,
Yeah.
but can't apply the concepts to new problems.
Exactly. Underfitting, on the other hand, is like that student who just didn't study enough.
So the model's just too simple.
Right. Too simple to catch all those underlying patterns in the data.
So how do we find that sweet spot, between capturing the useful trends and not getting lost in all the meaningless noise?
Well, that is the question, isn't it? Especially because real-world data is messy.
So how do we build models that actually work well on new data they've never seen before?
That's what we call generalizability, and I think that's a perfect place to pick up in part 2.
Welcome back to the deep dive. Last time, we were talking about how to create models that can actually work with new data they haven't seen before.
Right. And the lecture notes bring up a really interesting example about this. A study on the MERS outbreak in Korea back in 2015.
MERS. Yeah, that was definitely a big deal. But how does tweeting about it relate to building good models?
Well, the researchers actually created 2 networks. One to track the spread of information and the other to track the spread of the virus itself.
Oh, wow. So one for the online chatter and one for the real-world spread.
Exactly. They called them EpiNet and TweetNet. EpiNet was all about how the virus spread through, real-life interactions. And then TweetNet was all about the spread of MERS info on Twitter.
So they could see how the discussions online actually lined up with, like, the actual outbreak.
Exactly. And they found that, get this, the structure of TweetNet, especially the connections between influential users, could actually predict patterns in EpiNet.
Hold on. So you're saying they could analyze tweets and get insights into how the virus might spread?
Yep. That's the power of data.
That's incredible. So what kinds of insights did they actually find in the Twitter data?
One big thing was the role of retweets. The lecture notes mentioned that over 80% of the tweets in the study were actually retweets.
Well, yeah. I mean, if someone you follow shares something, you're way more likely to see it, right? And maybe retweet it yourself.
Right, and that's how you get these huge information cascades. A single tweet can reach tons of people super quickly through retweets.
It's like a chain reaction, but online.
Yeah.
Okay, but how does this tie back into, what was it called? Generalizability.
It shows that a model you train on one data set, like the Twitter data, can then make predictions about a totally different data set. In this case, the spread of the actual virus.
Got it. That's generalizability in action.
Exactly.
So if you build a model that can predict, like, retweet patterns really well, you might be able to figure out how information, or even a virus, could spread.
Yep. And this has huge implications for things like public health, right? Where understanding how information spreads can be crucial for dealing with outbreaks or even preventing them altogether.
It's kind of mind-blowing how something like tweeting can be connected to, like, epidemiology.
Right. It really shows you how interdisciplinary data science can be.
Definitely. And as we're talking about all this, I'm realizing that data science is so much more than just crunching numbers.
Yeah.
It's about asking the right questions, knowing the limits of your models, and always being aware of those potential biases.
Couldn't agree more. It's really a blend of technical skills, critical thinking, and, really understanding the subject matter you're working with.
And like the lecture said, not every problem even needs machine learning.
That's an important point. Sometimes a simple statistical analysis will do the trick. Or maybe you don't even need data analysis at all.
Right.
Maybe the answer is in qualitative research or talking to experts in the field.
It's like having a toolbox full of tools. You wouldn't use a hammer to, tighten a screw.
Exactly.
Yeah.
You need the right tool for the job.
And that's where human judgment is so important. Data science and AI are powerful, but they're not magic.
Right. They enhance our abilities, but they don't replace them.
And that brings us back to that question the lecture asks. What unique perspective can you bring to the table? What problems are you passionate about solving?
Such a good question, because at its core, data science is a human endeavor. It's about using our skills and creativity to tackle those real-world problems that actually matter.
Speaking of human endeavors, I think we could all use a little break. But don't worry, we'll be back soon to wrap things up and see what all of this means for you.
Welcome back to the Deep Dive. We're on the final stretch of our journey through data science and AI.
It's been quite the deep dive. We've talked about everything from the fundamentals of machine learning all the way to...
So those tricky parts, like model evaluation and how to make sure our models actually work on new data.
Generalizability. Right. And we even dug into that fascinating historical example from the 17th century Korean diary.
Yeah, that was a really cool way to see how our understanding of data has, evolved over time.
Definitely. But before we call it a day, let's bring everything together and see what it all means for you, the listener.
Sounds good. So where do we even start? Well, I'd say one of the most important takeaways is understanding those core building blocks of machine learning. Like, remember Tom Mitchell's definition?
Yeah, about how a computer program improves its performance with more experience.
Exactly. And we saw how that works in real-world examples, like creating a spam filter.
Or using tweets to understand how a virus spreads.
Right. But it's not just about building any algorithm, it's about building good algorithms.
Which is where bias and variance come in.
Yep. And remember, even something as simple as asking, are you a good person, can introduce bias.
It really shows how data science isn't as objective as we might think.
Right. Our own viewpoints and how we ask those questions.
They can really affect the results we get.
For sure. And then we have the two main types of learning, supervised and unsupervised.
Supervised learning is like having a teacher guide the algorithm, while unsupervised.
Unsupervised is more like letting the algorithm just explore and figure out patterns on its own.
Right. Predicting crap yields versus grouping those spam emails. Those examples from the lecture were really helpful to see the difference.
I thought so too. And then, once you have a model, you need a way to know how well it's actually working. That's where the confusion matrix comes in handy.
Ah, yes. The confusion matrix. It sounds intimidating, but it's basically just a way to visualize.
To visualize how well that classification algorithm is performing.
Yeah. It helps us see how many times the model gets it right, how many times it gets it wrong, and all the different ways it can mess up.
Exactly. But we can't just focus on the numbers themselves. We have to think critically about what those numbers mean.
Yeah, in the context of the problem we're trying to solve, like a 99% accuracy rate might seem amazing on paper.
But if that 1% error has some serious consequences, it's not good enough.
Exactly. So context is key. And then we have that broader idea of using mathematical functions to, model the whole world.
Right. It's a super powerful way to see those complex patterns, but we have to remember
that all models are simplifications.
Yep. That analogy of looking through a lens really stuck with me.
It's a good way to remember that we might be missing some of those smaller details. So we have to be aware of the limitations of our models.
And always be on the lookout for those blind spots.
Which brings us to the whole challenge of generalizability. How do we build models that actually work on new data they haven't encountered before?
The MERS Twitter study was a great example of that, right?
Definitely. It showed how data science can be used to understand and even predict real-world events.
Really powerful stuff.
But it also highlights how important it is to evaluate those models carefully and to really, really understand the subject you're working with.
Absolutely. Now, as we wrap up our deep dive, I want to circle back to that question the lecture posed to the listener.
About what unique perspective you bring to the table and what problems you are passionate about solving.
It's such a great question. Data science is more than just having the technical skills.
Right. It's a way of thinking.
A way of approaching the world with curiosity and that drive to understand how things work.
So as you continue exploring data science and AI, remember that your experiences, your insights, and your passions.
They're all incredibly valuable.
So go out there, ask those interesting questions, and see what amazing discoveries you can make. This has been The Deep Dive. Thanks for joining us, and until next time, keep diving.